Okay, y'all, today we're going to start out looking at this check your understanding, which my in-class students have already done. I'm going to go ahead and pull up the answer key for us to kind of take a look at it. Okay, something that all of the A, B, and C for the first problem have in common is they're all geometric, so we can kind of figure out what they are converging to if our R value is less than 1. On the first one, our R value is actually greater than 1. On this second one, whether it converges or diverges, we're looking at our p-value, so what is it, our exponent. And if our p-value is less than 1, then it diverges. Something that is true for all of these is that if our limit, or if the series converges, so like on this one, my A and my C here, if the series converges, then the limit for sure goes to 0. But the converse of that is not true, because if our limit goes to 0, our series doesn't always converge. And a perfect example of that is our harmonic series. Well, we talked about up here, harmonic series, that diverges even though this limit does go to 0. So if it converges, if the series converges, then that means that our limit will also converge. Today we're going to be looking at saying that in a different way. Okay, we actually call this the contrapositive statement. So if a series converges, then the limit also goes to 0, but if we negate the the last part, so if we say the limit does not exist or it does not approach 0, then not this. So then the series would actually diverge. So this is a statement that is always, always true, and we can actually check this for divergence. If it does go to 0, or it converges, that doesn't mean that the series is going to converge or diverge. This only tells us if this condition is true. If our limit doesn't approach 0, then we know the series for sure diverges. So if we're kind of checking this one right here, we can look at the limit of it, and the limit doesn't exist, so then we know that the series is going to diverge. And this one right here, our limit ends up approaching our coefficients, 1 over 2, since it's the same degree on top and bottom. We could even use L'Hopital's right there. But it ends up approaching 1/2, that is not 0, so then we know that this diverges. Both of these diverge. And this is not true, again, in the converse way, and the harmonic series is the best way to actually look at that. So if I look at my sequence right here and I look at my limit as n approaches infinity, this is actually going to approach 0, but our infinite sums of this is actually going to diverge. So this doesn't actually tell us anything. It's when it doesn't approach 0 or it does not exist. Let's take a look at these two examples right here. So if I'm looking and I'm trying to use my divergence test here, I'm going to look at my limit as n is approaching infinity of cosine of 1 over n squared. And so inside of here, my 1 over n squared is going to get really, really, really small because I'll have 1 over a huge number. So this right here will approach 0. So my answer will actually be cosine of 0, which is 1. That's not actually 0. So we know that since this doesn't actually equal 0, that this is also going to diverge. Let's try that with our second example. Our limit of 1 over n, as n approaches infinity, this square root is going to get huge on the denominator, and I'll have 1 over a really, really big number, so the whole thing will actually end up approaching 0, but that doesn't tell me anything about this right here. It doesn't actually tell me if it converges or diverges. It could be either in this case. This next test that we can do, there's a couple of conditions that we need to have. So not only does our function need to be continuous and decreasing, but it also has to be written in some form of a sequence. So our infinite sum, either and our improper integral over here of the same function and of the same series are either both going to converge and or both diverge. So these two are linked. These two are linked to each other as long as these conditions are true. So functions that this like wouldn't work on, sine of n for n equals 1 to infinity, that would not work because it is not always decreasing. We need something that is actually going down or approaching 0. And here's kind of an example of why. So if we compare this to just our partial sums or our limit of our partial sums that we have here, eventually we will end up looking at all of our area underneath that curve, which is exactly what this is saying. And since this converges, then our series 1 over n squared is also going to converge. So it is decreasing over time. It actually hits all of those conditions up there. It's decreasing, it's continuous. My function is also can be written as a sequence. So if this converges, then this also converges as well. We don't know what our series converges to, but we do know that it converges. And again, I really can't say this enough. Just because one thing converges to a number, like 1 in this case, this is not actually going to converge to 1 right here. But we can just determine whether it converges or diverges by also looking at its improper integral. So here if I look at my integral of 1 to infinity of 1 over x to the third power dx, and this is an improper integral, so I'm actually going to have to use my limit as my upper bound here approaches infinity. So as b approaches infinity of 1 over x to the third, but I can really write that as x to the negative 3 dx. Now I can actually take that integral and I'll leave my limit as b is approaching infinity out in front. So x to the negative 2 and then divided by negative 2, so negative 1/2 out in front, and I'm evaluating this from 1 to b. So this will tell us if our series up here converges or diverges by if this converges or diverges. If our integral converges or diverges. So I have negative 1 over 2, and then this would be an x squared, but I'm plugging in b to that, and then minus another negative 1 over 2, and then 1 squared. So it looks like as b is approaching infinity, this thing is also going to approach 0 because I'll have 1 over a really, really, really big number. Looks like this is just going to approach 1/2, which means that it converges, which also means that this converges. I want to take a look at this next example here. So use the integral test to determine if this whole problem converges, and so I'm going to take my integral of 1 over, I'm just going to do square root of x, so because this is not a sequence anymore, from 1 to, normally this would be infinity, but I'm going to write it as a b and then take my limit as b actually approaches infinity. Let's go ahead and follow this through. Okay, so if I follow all that through, I end up getting my limit as b is approaching infinity of 2 and then square root of b, and that's just going to keep on getting bigger and bigger. So that's actually going to approach infinity, which means that this diverges here, and so this is, my series is also going to diverge as well. These are two problems that you may see either in your take-home test or on your practice. So I just wanted to give you some more examples. And then kind of our last one that we're going to use, or we're going to talk about looking at our integral test of, is would this actually work? Like, could I take a look at my limit as b is approaching infinity from 1 to b of negative 1 to the x plus 1 over square root of x, and if we go back to our conditions up here, sorry I'm scrolling, if we go back to our conditions, our function has to be strictly either increasing or decreasing. And in our case, because this is an alternating series, it's alternating back and forth between 1 and -1, it is not decreasing. So it does not satisfy our double I condition. I feel like we already formally defined our P series because when we were talking about our harmonic series 1 over n, that's when we end up finding out that this diverges. But if I look at any value, so like n to the second power, that actually converges. We don't know what to n to the third power, 1 over n to the third power, because it is still getting large, but it is getting large in a very small way. That feels funky. This does converge, and we can show that via the p-test. So like this last one, our p-value would be 5/4. That is something bigger than 1, so we know that this is going to converge because my denominator is going to get big fast enough. Our very last part that we're going to be talking about today is like, hey, we're adding these infinite things together, but how good of an estimate is that? Like, how far off are we from the actual estimate or the actual value of an infinite sum of things? And I found this video right here by Dr. Trefor Bezzati. I would highly recommend watching this. It's just like a 9-minute video. He just goes through it very, very elegantly of like how good of an estimate is it. So I highly recommend this. And I kind of skipped ahead. So like here's our partial sums, S sub n, and then here's the rest of it. So we call that the remainder off of our partial sums. So this is the part that we're trying to get significantly small, either by saying, hey, this has to be less than 0.01 would be common in like a stats class. But how big is that error? It's still an infinite number of things, but how far do we even have to go out in order to have this a certain amount of error? And if you do watch that video, it kind of corresponds to this formula that we have right here. So we're saying that our remainder, those following amounts that I have, can also be equal to if I take my infinite sum and subtract off my partial sums, then I'm just left over with that sum starting right after my S sub n, so my sum from n plus 1 back on. So this right here is this is my error that I'm actually trying to find. Here's a good visual representation, but I actually want to jump to an example, and I think it will be more clear when we look at an example of this. Okay, so we could be here for a while if we actually wanted to add and find my 10th partial sum, because I would have to plug in 1, and I would have to plug in 2, and I would have to plug in 3 to this equation, add them all up, and then I would also have to plug in 10 to this equation. But Desmos actually makes it really easy for us. So here I'm on Desmos, and I want to do a finite sum. So if I type in the word sum, I can go from 1 to 10 of my equation was 1 over n to the third, and that actually adds them all together. That is my value. Okay, another way that you can do this is by going into the calculator function, scrolling down to calculus. Here's my also summation, and now I'm just going to go out as like far as I possibly can to see what the true value is going to be, what it estimates it of. It doesn't go out super far. So like this is what Desmos is estimating to be the true value right there, and it's not really changing a whole lot, so it's approaching that. Well, like how far off are we? And we can actually use an indefinite integral to figure that out. And I just really want to reiterate too that Desmos only does finite sums, and so this is not the infinite sum. It's approaching, like the infinite sum would be approximately that, but it is not exactly that. So using the idea from the video, we're trying to estimate the error between S sub 10 and actually the true value of that. So if I'm trying to estimate the error between those, then I'll probably want to end up subtracting them. So Here I'm taking my full-on series and I'm subtracting the first 10 partial sums, and what I'll be left over with, my sums that come after that 10th one. So it's still going to be going towards infinity, and here instead of starting at 1, we're actually going to be starting at 10 and then going out. And this right here is actually going to be an improper integral. So I can look at my limit as, I'm going to say here, as b is approaching infinity from something up until b. And this down here will actually just be my 10 because I'm looking after 10 of 1 over, I'm just going to use an x to the third dx because n is usually associated with my sequence. And now I can actually solve this. So I'm going to bring this up to be an x to the negative 3 right there. And when I take my integral of that, I will have x to the negative 2, 1 over negative 2. And now I can plug in 0 and I can plug in b. So that's what I kind of get when I plug in those values. Again, I'm using improper integral. As b is approaching infinity, my denominator is going to get huge, and I'll have 1 over something huge. So that'll actually just become 0. And so it looks like my error right here is just going to be this number, which ends up being, I think, exactly 0.05. And we can actually see that this is way further off than we actually anticipated. So that's not even a good estimate. Okay, so my 10th partial summation, I will be 0.05 or 5% from the entire infinite series, which actually isn't so bad when we think about that because it's only 5% off. But what if we were trying to be really, really accurate? How far off would we have to go in this series in order to actually get whatever remainder is after that? So I'm going to say just capital N to the third power. Whatever remainder after that would be, this whole thing would actually be less than 0.001. So really a small error value. And once again, this is like our nth partial sum, but it's like capital N partial sum, so different than a lowercase. We kind of actually did all of the work to be able to do that. So if I look at my integral from up here, I have my limit as b is approaching infinity because this really is approaching infinity over here. But if I look at my remaining start value, it's actually starting right here at capital M, and I do my same whole thing that I actually did up here, I will end up getting, so like dot dot dot, 1 over 2 to the bth power squared. This is my limit as b is approaching infinity. And then plus 1 over 2 when I plug in now my capital N, I'll have like capital N squared. This thing still ends up approaching 0. So this is how large this is my error that I would have right here. And I actually want that error to be pretty small. So I want this error right here to be something that would be less than or equal to 0.0001. And now this is just turned into an algebra problem to actually solve. I am going to multiply times n squared on both sides times n squared over here to cancel that out, and then I'm also going to divide by 0.001, and I should get that n squared has to be bigger than or equal to, I think it ends up being 500 over here. And now this is still an algebra problem, so I'm going to take my square root. So n has to be larger than or equal to, it's like plus or minus, but the minus one doesn't really make sense, so we'll just stick with the plus, 22.360. And n has to be bigger than that. So if it was 22.4, that would be big enough. n is going to be an exact value because this is a sequence. So I'm going to round up to my next whole number. N is actually going to be equal to 23. If I round down, my error will be bigger than this 0.001. Okay, so for your hints that we have here, you can definitely use p-series to show that this converges. My hint for this one is to look at the integral of that series or of that sequence that I have up here as b is approaching infinity. So this will be like our b value. And then a smart thing to do would be you can either keep this as an n, or we're looking for the lower and upper bounds for the remainder, so you could also keep that as 1,000. That would be our lower and our upper bound. This last question on here, it feels like your answer is really, really wrong because it ends up being huge. So this is a very large number. And you can just write it as like 10 to the somethingth power, if that's helpful. Okay, on this very last problem, there is actually one of each of these within here, and then also 2 converge and 2 diverge. Okay, y'all, hope that's helpful. Bye.